Here I have like a figure giving some intuition in a binary classification model. So as we can see here, it's panda versus gibbon. So the dashed line here is the decision boundary of this model. We classify image and to be either a panda or a gibbon. So the blue point X here on the bottom is the original example. It is a panda image and it's correctly classified as a panda. Then we add a perturbation to the original example to move it across the decision boundary to the gibbon region of this model as the red point X prime. And this perturbation is actually so small that the noise added is imperceptible for human. So the X prime, the adversarial example still looks like a panda for us. However, the model will just misclassify X prime as a gibbon. So let's take a deeper look at this example. There are actually many ways to perturb the original example across the decision boundary to change the model's output. However, there's an optimal X star, which is the closest point to the original X among all points that are classified as a gibbon. So we can define this point as the minimum distance adversarial example, and the corresponding perturbation distance is denoted here as epsilon star. So for any other X prime which are classified as gibbon, the perturbation distance is epsilon u, which is larger than epsilon star. On the other hand, for all points that are closer to the original example than the X star, the model's output should not be changed. So we can draw like a circle with radius epsilon L around X, such that the epsilon L is less than the epsilon star. So as long as the example as long as the points is perturbed the distance is like less than epsilon L, so the point is still in this circle, the model's output should be the same as the original X. So here we have basically 3 epsilon values. The epsilon star is the minimum distance we need to change the model's output. It can be used to measure the robustness of this model at this specific point X. However, it's usually very hard to solve. So for example, in neural networks or like in tree-based model, we already have like some prior works proving it's NP hard to solve the epsilon star value. So when we do adversarial attacks, we actually find an adversarial example X prime and its corresponding epsilon u, which is the upper bound of this epsilon star. And in another like category of problems, the robustness verification will try to obtain a lower bound of epsilon star, the epsilon L, such that the model's output cannot be changed as long as the perturbation distance is less than epsilon L. So from here, basically, it leads to 2 important questions in this area. The first one is adversarial attack. So basically, how we generate adversarial examples to fool the model. And we can generate this kind of example for different kinds of model, for image recognition, for NLP model, for speech model, all sorts of models. And the second one is verification problem. Basically, how we evaluate the robustness of a machine learning model by providing a safety region like the epsilon L circle, like this kind of region. And the important area in this community is like adversarial defense. So basically, we know how to generate those bad examples. We know how to give you safety regions, and we try to train a model with better robustness, basically. And finally, there are like some applications. So we can use those kind of robust model as building blocks to other applications. So in this talk, I'm gonna present 4 of my works during the past few years. Basically, they are in adversarial verification problem. So we have like a the robustness verification for tree-based models. In defense, we will present like a defense also for tree-based model, and we'll have like an empirical study on the robustness of deep learning model. And finally, I will present one of my pretty recent work on robust reinforcement learning. Just use the robust training method to build like robust reinforcement agents. So first, I'll present the robustness verification method and design specifically for tree ensemble models. So among all machine learning models used in practice, tree-based model actually stands out in many applications, and they achieve state-of-the-art performance. So here, a survey among the teams that rank like top 5 from Kaggle in 2015 shows that tree boosting packages such as XGBoost or like LightGBM are like second or third most popular packages used by the participants. However, adversarial robustness for tree-based model is largely unexplored in the literature. So for tree-based model, we still have like the 3 problems: adversarial example, or like minimum distance adversarial example, and robustness verification. For generating an adversarial example for tree-based model, there are like many recent works work on this problem, and basically they're based on sort of like a search-based attacks. For finding minimum distance adversarial example, there is a previous method which use mixed integer programming like optimization problem, which we call like a MILP, to solve the problem. So you can solve the exact minimum distance adversarial example, but like mixed integer programming is NP-hard. But it can be very computationally expensive when the model is large. So here I will present our recent work on how to fast to run a robustness verification for a tree-based model to find a tight lower bound for the epsilon star. And note here, in this thesis, we mainly focus on L infinity norm. So in L infinity norm, a ball or like a circle actually looks like a square box. So for simplicity here, we use a binary classification in our introduction. The class labels basically are +1 and -1. First, we consider a single decision tree. We assume each leaf has a numerical output value, and we do a binary classification based on the sign of the output value. For example, here an input arrives at a leaf, and its corresponding output value is 1.4. So it's classified as class +1, +1. In decision trees, the leaves, basically, you can regard the decision tree leaves as a partition of the feature space. So you partition this feature space into a collection of disjoint boxes, and the output value is basically determined by which box the input falls into. The partition of this decision tree can be parsed in linear time, basically, using just like a DFS, like a depth first search. Then giving a adversarial perturbation budget epsilon. So basically we just pick an epsilon value, and we only consider the adversarial perturbation within this epsilon radius L infinity ball. So we can just only study the boxes that are reachable by this perturbation in L infinity ball of radius epsilon. Then we check if the output can change its sign when the input is perturbed in this L-infinity ball. So for example, here in the figure on the right, the original X, its output is 1.4, which is positive. But when we perturb, we can reach another leaf, and after that leaf, the output value is minus 0.5, which is negative. So the model's output label can be changed. And if we can change the output label, basically we just reduce epsilon value. Otherwise, we increase this epsilon value. And this can be done in a binary search way. And we can get an approximation of the exact epsilon star for any given precision. But like the question here is like, how about an ensemble of trees? So we have like many trees in our model. For example, here we have like 2 trees. And the ensemble's output label is determined by the sum of each tree's output value, and we take the sign of the final output of this ensemble as a class label. So in this example, the blue tree outputs minus 0.8, and the red tree outputs 1.4. So sum up, we get like a positive value, which means this input is classified as class +1. So, but the question here is that different trees, they may have like different structure, and so they have like different partitions of the feature space. One possible way to solve this problem is that we can merge the 2 partitions. We can calculate all possible intersections of the boxes and calculate the value of each smaller box by summing up their corresponding leaf values. And then we can basically follow the same procedure of verifying a single decision tree. However, the number of boxes will increase exponentially with the number of trees. So when we have like a very large model with many trees, this method is going to be intractable for computation. So to solve this, basically our strategy is to divide the trees into groups. When we have k trees in an ensemble, we divide them into m groups. Then within each group, we merge the boxes. And we pick the minimum value in each group's result to sum up the minimum value and then we sum up the minimum value in each group together. If the sum is greater than 0, then the model's output is guaranteed to be unchanged, as long as the perturbation is in the L-infinity ball with radius epsilon. So for example, here we have 4 trees. So we divide like the blue tree and the red tree as one group, and the orange tree and the purple tree as another group. So for the blue tree and red tree, we merge all the boxes and we pick the minimum value we can get, which is 0.1. And for the orange tree and the purple tree, we do the same thing. We merge all possible boxes, and we pick the minimum value, which is minus 0.05. We add these 2 values together, which is plus 0.05, which is positive, which means the model's output is still guaranteed to be class +1. Because here we make a very conservative on the worst case. We only pick the mean from each group instead of calculate the mean for all the trees altogether. So after the binary search, the epsilon value we get is going to be smaller than the actual exact value epsilon star. So we'll get like a lower bound for robustness verification. So note that here, if the model's original input has label -1, we actually pick the maximum for each group instead of the minimum of each group. So this method can be extended to a multi-level verification framework. So as mentioned before, after merging trees in each group, we can terminate the merging, and instead we summing up the minimum value in each group to get a lower bound Or what we can do is like we can merge the boxes again from each group before picking the mean. In this way, we'll get a slightly tighter bound. So here we show the experimental results of our method. The red bars here are our method, and the blue bars here are from an adversarial attack method. So for better comparison, on the left figure, we show the bound value normalized by the ground truth epsilon star value calculated by MILP. Because we are solving the robustness verification bound, basically our red bars are always less than 1. But we can see that the red bars can actually serve as a very tight lower bound for epsilon star. On the right hand, we show the running time. Again, for better comparison, we normalize our running time by the running time of the MILP. So we can see that our method can be up to around like 10,000 times faster than solving the MILP. So this is for robustness verification for tree-based models. And for the second part, we move to adversarial defense. In this section, I will present our work in adversarial defense for tree-based model and some empirical studies on the robust deep learning models. So just as deep neural networks, adversarial example also exists in tree-based model. So this figure basically demonstrates the adversarial example for 200 tree GBDT models. And we tested on MNIST or fashion MNIST dataset. We can see that if we add a small noise with a very small distortion to the image, the model's output will be completely changed. So first here, I'll give some intuition why tree-based model are still pretty vulnerable. So here's a toy example, a special case toy example to give some intuition. So intuition is the best accuracy model may not necessarily to be the best robustness model. For example, here we have 10 data points with 2 labels. We do a binary classification. And basically they are blue labels and red labels, 2 classes. So let's say if we are only allowed to build a depth 1 tree, so just one single split to classify these examples. So as the root node of this tree, if we do a binary classification and we're only making 1 split in the root, our best split for accuracy is actually going to be to split the data points using feature x2. In this way, we'll get 80% of accuracy for those 10 points. However, the problem here is that with this split, all the data points are so close to the decision boundary, and they can be easily moved to the other side of the decision boundary if perturbation is allowed within a small L infinity ball around each point. So in the worst case, our accuracy will be if we allow to perturb all the 10 data points. So is there a better split for robustness? The answer is yes. So we can choose feature 1 instead of feature 2. So we can draw a vertical decision boundary along the feature x1. This, for example, here, if we draw the vertical decision boundary, we can split the data point together with the L infinity ball around them. In this case, the data points are far away from the vertical decision boundary, and we can guarantee to get 70% of accuracy, even if the data points are perturbed within the L infinity balls around each original point. So in the original decision tree training, basically at each node of the tree, we split the training set into 2 parts, and we put those two parts into left or right child node of this this root node. This split is determined by the training example's value, like feature value, on a specific feature with a specific threshold. So basically what we do is like we pick a feature value, we sort all the training examples according to that feature value, and we just sweep through all possible threshold, and we pick the best one. Here, J is the feature index, and eta is the splitting threshold. At each node, we try to find the best feature threshold pair. To find this best pair, we maximize a score function, and different like tree-based method will choose like different score function. So in our proposed robust decision tree training framework, instead of maximizing the score directly, we maximize the worst case score when the perturbation within within the L infinity ball is allowed on the training data. So a robust score is determined as the minimum score of current split under all possible perturbations of data within epsilon L infinity ball. So interesting, this is actually a 1D problem. Given a specific feature J and a specific threshold eta, for perturbation in an L infinity ball with radius epsilon, only points within eta plus or like eta minus epsilon can be perturbed to the other side of the decision boundary. Points outside this ambiguity set are certainly placed on the left or on the right child under perturbations. So the adversary's job is just place the points in this ambiguity set to the left or right child to reduce the score of this split. However, there are exponentially many possibilities, since each point in the ambiguity set can be placed in either on the left child or on the right child. So for simple score functions such as information gain or gain impurity, we can approximate the adversary's optimal strategy. For complex score functions such as the score function for XGBoost, this can be a 0-1 integer programming problem, and it's very hard to solve. So instead, we use like a very rough approximation here. We only consider like 4 representative cases to approximate the robust score, and this approximation does not increase the complexity of original decision tree training algorithm. These 4 scenarios are basically no perturbation, or we put all points in the ambiguity set to the left, or we put all points in the ambiguity set to the right, or basically we just swap the points in the ambiguity set. So this seems to be like a very rough approximation, but how well does it work? Surprisingly, it works pretty well. So now let me go over to the experiments. Again, blue bars are our proposed robust models, and red bars are original natural decision tree training method. Decision tree training method. We train gradient boosted decision tree on 10 data sets, including some popular data sets such as MNIST or Fashion MNIST. They are used for evaluating the robustness of deep learning models. On the left figure, we show the test accuracy of naturally trained tree ensembles and robustly trained tree ensembles on clean data sets without adversarial attacks. So we can see that our method achieves similar test accuracy as the natural models. On the right, we show the average L infinity distance of the adversarial examples found by an attack. So the larger the distortion norm indicates a better robustness. So if the bars are taller, then the model is more robust. So we can see that our blue bars showing that our robust model can significantly improve the robustness under adversarial attack. So what about defense in deep neural networks? This problem is still, so the defense for neural networks is still a largely unsolved problem. And we have seen the number of adversarial robustness papers grew exponentially during the past few years. So there are like many existing works trying to build robust deep learning models, but a lot of them lack theoretical guarantees. And many heuristic defense methods have been proven ineffective. Also, the computation cost for training robust deep learning models is pretty high. It's actually unclear if efficient robust training method actually is possible or not. So there are like some existing works suggesting that training robust deep learning model may require more training examples or more computation time. Finally, existing robust training method can only improve robustness on training set, and the performance may be worse on the test set. So here we have like some empirical studies on the practicality and the hardness of a state-of-art defense method on deep learning, which is adversarial training. We show that the effectiveness of adversarial training has a strong correlation with the distance of a test example and the manifold of a training set embedded by the network. So in this figure, the x-axis basically it's the distance of a test example and the training set. The blue bars here show the attack success rate. So the lower the success rate, the model is basically more robust, and the higher success rate, the model is vulnerable. We can see that the test examples that are relatively far away from the training set are likely to be vulnerable to adversarial attacks. And here the blue bars shows the distance distribution in the test set. So we can see that the most test examples are relatively close to the training set, but the test example which are vulnerable are in the like long tail of this distribution. So moreover, if we slightly change the distribution of the test data, for example, for clean like images, we can change the clean images brightness or contrast slightly. And after we change that, we basically slightly modify the distribution of test data set. And after this modification, adversarial example with low distortion can be found. And basically the state-of-art defense method can be easily broken. So finally, I will present some applications for robust machine learning model. This is the last section of this talk, and it's about using robust model as a building block to build robust reinforcement learning. So in deep reinforcement learning, researchers also have shown that adding a small adversarial noise to state observation can successfully attack the agents trained using like different RL algorithms for many tasks. So agents can be easily fooled and receive a dramatically low reward. All these attacks follow the same setting of perturbing state observations, where an attacker adds a small noise to what the agents observe, but it does not change the true state where the agent is. This wrong observation leads to wrong or like suboptimal actions to the agent. For example, here we show a toy example of car navigation. In this car navigation scenario, here the green icon is the true position of the car, and the red icon is the observed position of the car under uncertainty. So because there's like some deviation of the in the observed position, the car may turn left too soon, and it will crash the wall basically. So in this work, basically we want to learn a robust policy, which is able to achieve high reward, even when there's a strong adversary perturbing the state observations. Obtaining a robust agent sometimes is more challenging than in the supervised learning setting, because there's no this kind of ground truth action or like ground truth label in reinforcement learning. So in this work, we first developed a theoretical framework for this problem, which we called state adversarial MDP or SA-MDP, to characterize the setting of perturbed state observations. In SA-MDP, the adversary nu adds a worst-case bounded perturbation to the agent's state observation, but it does not change the true state where the agent is. We assume that given a state S, the bounded perturbation is in a set BS. For example, we can assume this BS is an L infinity ball around S. So we can naturally define V function and Q function for a given agent with policy pi under adversarial perturbation nu on its observation. So our SA-MDP characterizes the worst case adversarial perturbation on the state observation, so the adversary always minimizes the agent's reward. Then our goal in SA-MDP is basically try to find an optimal policy under the optimal adversary, which is the maximum problem. It is actually pretty hard to solve the optimal SA-MDP policy directly. But we prove that if we can bound the distance between the action distribution of the original state and the action distribution under adversarial perturbations, the performance loss caused by the adversary in SA-MDP can be also bounded. So here the distance is measured by total variation distance, this DTV. So intuitively, this theorem says that a policy that is not sensitive to state perturbation can be robust under adversary. Basically, for a robust policy, we want to sort of like map two states, S and S prime, which are close to each other, to two actions that are also close to each other. So we want this A and A prime to be closer to each other, so that it's not sensitive to the perturbation in the input state. So if the action space is discrete, for example, in DQN, we want the A and A prime to be the same, basically. So this theorem basically inspires us to use a regularizer to improve robustness under adversarial attacks, which in general requires us to solve a mini-max problem to find the policy that has like small maximum divergence under state observation perturbations. So here we present the implementation of this idea in DQN. In DQN, so the action space is discrete and finite. So we use a neural network to learn the Q function, and each output logits of this Q value, each output logits of this neural network is the Q value of an action. The agent chooses action that has the maximum Q value. So DTV distance between two policies is 0 if they take the same action, and 1 as Then our goal is to learn a Q function whose action with the largest Q value does not change. If the input has, if there's some perturbation in the input. So for a given state S, we assume this optimal action at the original state S is A star S. We define like a SA regularizer. So this additional loss basically first calculates the maximum distance between the Q value of actions other than A star and the Q value of A star. Then we take another maximization among all perturbed states, S hat in BS. This regularizer is added to DQN's loss, and the training procedure of DQN is unchanged. We call this SA DQN. So basically, they are like basically the hard part is to solve this additional regularizer, the L tilde term in SA DQN. So there are like two different ways to solve the L tilde. The first one is to use a technique which is similar to adversarial attack. We keep the model fixed, and we run projected gradient ascent on the S hat to solve a lower bound of L tilde. The second way is to use sort of like a convex relaxation-based neural network verification tool to solve an upper bound of L tilde. Basically, convex relaxation of this kind of tool, basically they relax the non-linear units in neural network, and they enable us to have like a pretty efficient analysis on the output bounds of a neural network. And there are like many works working on this. There are like many works provide us the tools to do this kind of relaxation. And it's worth to mention that in practice, we actually use a hinge loss by adding a constraint on the minimum value of this L tilde. This lower bound on L tilde basically stops us from keeping optimizing the regularizer too much when the safety margin is large enough. So for another reinforcement learning algorithm for this kind of PPO algorithm, basically the action space is continuous, and we use like a neural network to learn the policy directly. And the policy is the Gaussian distribution, and the neural network's output basically is the mean of the Gaussian. Here, the regularizer, instead of penalizing the DTV distance, we penalize the KL divergence for simplicity. And this regularizer can be similarly solved as SA-DQN, and we call it SA-PPO. So for the for experiments, so for DQN, we test our method on 4 Atari computer games. And the observation of the agent is basically the pixel value on different frames of this computer game. In this figure, on the left, the gray bars are vanilla DQN agents, and those bars with hatches on the right of each figure, they are SA-DQN solved by like the projected gradient descent method or like convex relaxation. We can see that our SA-DQN method has a very low impact on the agent's performance in natural environment without adversarial perturbation. However, when under attacks, our method can significantly outperform the existing method using adversarial training or like robust imitation learning in most environments. Sometimes we can improve by a large margin. And the video on the right is a example in Atari game, which is called Roadrunner environment. So in this example, the SA-DQN achieves like nearly perfect score and the vanilla decoding can only get like 0 points if we have attack on the frame. So for PPO, we test our method on like 3 Majorco simulation. So Majorco stands for multi-joint dynamics with context. So basically, it's like a small simulation environment for robot control. And our observation can observation are basically physical values of this robot, like the physical value in this kind of dynamic system, like velocity or like position of the joints. So for PPO agents, our robust regularizer can sometimes even improve the agent's performance in a natural environment. So basically, without any attack, if you have like this kind of robust regularizer, your agent can actually achieve better or like higher rewards than the natural PPO agents. Again, in the gray bars are the vanilla PPO agents, and those 2 bars with hatches are SA-PPO agents. So when under strong attacks, our agents can significantly outperform other baseline and remains robust. On the right, we show videos of a humanoid environment. So we can see that for the vanilla PPO agents, they can barely stand up, but our SA-PPO agents can successfully walk for a very long way. So as a conclusion, basically the contribution of this thesis, we propose robust training and robustness verification for tree-based model. We have like some empirical studies on the limitation of robust deep learning models. And finally, we show some applications of robust deep learning models for robust reinforcement learning. There are like some takeaway messages of this thesis. The first one is like when it's hard to find the exact value, basically we just try to find its upper bound and lower bound. This is exactly what we do for finding adversarial example. So we cannot find the exact epsilon star. So we find its upper bound and lower bound. And the second takeaway here is training robust model basically requires a smart objective function. We just change how we train the model, basically. And sometimes this modification needs minimax optimization. So for future directions, there are like many future directions in my mind, but these 3 are the most important one. I think the first one is like a metrics for robustness beyond LP norm. So currently in this community, basically we just use LP norm to measure the robustness. We just measure the LP norm of the adversarial example and the original example. However, like there are like some other norms we can use. For example, we can do spatial transformation of the figure. We can do some semantic modification. So there are like some other metrics we can use. The second one is like an adversarial example and robust training can sometimes improve the model performances, even when there's no adversarial attack. So this is like a pretty surprising phenomenon. Basically, when we train robust model, we add regularization to the training. This regularization can sometimes improve the model's natural performances. And finally, there's like some vague connection between robustness and interpretability of the model, which are also pretty interesting. So finally, I want to say thank you to my advisor, Professor Duran Boney. I'm extremely grateful for this opportunity he provided me to work with him in the past 5 years. And I also want to say thank you to my committee members, Professor Daniel and Professor Shah, for their advice and comments on my research and on this thesis. Also, I want to say thank you to all my collaborators, my mentors, and the people who helped me in the past 5 years. Without their help, this thesis is going to be impossible. And also a big thank you to current and past bonding group members and all my friends at MIT. And finally, and most importantly, I would like to thank my parents and my family. They always provide me with strong support from China. I really appreciate your love and your effort to bring me up to be a better individual. So that's the end of this presentation. Thank you very much for your attention.